Okay, so this is what we have. We said if we look at our notes, that our notes tells us that if we have one that's odd, that's the one that we should look at first, right? And so cos to the third was odd, so that tells us we're going to save one of them. Okay, so I'm going to save one of the coses. So I'm going to do cos times cos squared. So I saved this one. And then it tells me what I'm going to do next is I'm going to look at my blue sheet and I'm going to take the cos squared and I'm going to use the Pythagorean identity to convert the cos squared into sine. So that I have the sines I can use u substitution on, and the cos will be the derivative of the sine. Does that make sense? So if you look at your Pythagorean identities, cos squared equals 1 minus sine squared. Okay, so I'm going to leave the cos x in the front. Cos squared is 1 minus sine squared. Then I've got the sine to the fourth. Well, think about your pre-calc unit where you did trig proofs. There was a whole host of things where you were showing that you could do substitutions and prove that things equaled other things. That's exactly what you're doing here. Is you're just substituting things out. Lots of things equal other things. It all goes back to triangles with trig. How you can substitute things out. Things equal, like sine equals 1 over cosecant, cosecant equals 1 over sine, sine squared plus cos squared equals 1, all those sorts of substitutions. So there's lots of different things you can sub out, but it goes back to pre-calc with all those proofs that you guys used to do. So if you want to know so all I gave you guys in the video last night was there was a proof for that. So if you want to know where that comes from, you just have to look up online where that proof is, and then you'll know where it comes from. Yeah. Okay, so let's go ahead and we'll take the sine to the fourth and we'll distribute into this. So we've got cos x, and then this would be sine to the fourth minus sine to the sixth. Are we okay with that? So I just used exponential rules multiplying there. Okay. So at this point, I just turned this into a u substitution problem. So what is my u? Sine x. What's my derivative of u? Cos. Okay. Huh? Well, if you had u is sine to the fourth minus sine to the sixth, then you would have to do that whole chain rule is your derivative. And you're not going to have that derivative there. So if I just say that u is sine x, then I can say the derivative of u is cos, and then there is the derivative there. But if I say u is sine to the fourth minus sine to the sixth, then I have to have the whole chain rule present for my du. And that's not going to be the case. Minus u to the sixth. What do you mean earlier? Because up here, if you did this, you'd have to use the chain rule. If you said that your u is sine x up here, the derivative of sine to the fourth, if you did u up here equals sine x, the derivative of that is cos, not cos to the third. So you can't do it in the beginning. Does that make sense? Okay. So that's the issue, and that's why we have to get the problem where we got it, is because because of your exponents. You're having issues with exponents here, so we're manipulating the problem so that the exponents are something we can work with instead of having exponents being something we can't work with. So what we did is we made it so the exponents became something that were just on the u instead of something that were on our derivative. We took the exponents away from the derivative, away from the cos, and we put them just on the term that we were going to use as u. Does that make sense? Okay. So now we can say we've got our u, we've got our derivative. So now the thing that we're integrating is u to the fourth minus u to the sixth. And then this is your du. So u to the fourth minus u to the sixth du. All right, how are you guys feeling about that? Okay, so when we do our antiderivative, what do we get? Let's see, good. And then we can go back and replace the u with what we know u equals, which is sine x. So we're going to say that this is 1/5 sine to the 5th x plus 1/7 sine to the 7th x plus c. Oh, minus, thank you. And if you want, you can go back and like switch the order, you know, since your highest exponent is 7, like I wrote it second, but if you wanted to put that first, you could put that first and put it in the correct order, but a lot of, like when I was checking answer keys and stuff, a lot of people would put it second because it became second. It's not a big deal. So kind of like the idea of FRQs, that they'll take a lot of forms of the right answer and call it good. Same sort of thing with this. It's not that big of a deal. They get a lot more relaxed the higher up in math you go. So if it's not in standard form, they don't care so much. Okay. All right, did that warm up our brains a little bit for today? Okay, so now we had some even exponents there, but we didn't have to do the power reducing formula. Can somebody tell me why we didn't have to do that? They weren't all even. Yeah, so we were able to do u substitution. So the only time you would have to do the power reducing formula is if, let's say, there was not a cos here, we were not able to do u substitution, and we were only integrating even exponents. If we were just integrating sine to the 4th minus sine to the 6th, then we would do the power reducing formula. Does that make sense? So as long as we're doing u substitution, we don't have to worry about the power reducing. But if we're doing u substitution, then we don't have to worry about the power reducing because we're doing u substitution. So you're not doing both in the same problem. It's one or the other. It's two different strategies. Does that make sense? Okay. All right, so your assignment is that Larson page 1359, and then once we have done either a little bit less than half the class, because we do have to take notes, so a little bit less than half the class, once we get a good handle on that, then we're going to switch over and do the secant tangent ones. Strategies are very similar, but slightly different. It's still the Pythagorean identities. It's still keeping in mind the odd versus even exponent idea, so we can, you know, save something for the derivative and do that sort of thing to do the problem. Okay, so go ahead and get started. The secant tangent is not, we didn't start with secant and tangent because it's not quite as nice. So if you think about it, the derivative of sine is cosine, the derivative of cos is negative sine. So that's a nice, just like direct kind of relationship. What's the derivative of secant? It's not just tangent. It's secant times tangent. So when we look for that one, it's going to be a little bit different because you're not just going to be saying, oh, if I want the secant to be the u, I'm just going to have a tangent sitting there. No, I need to have one secant and one tangent sitting there. Does that make sense? Okay, if I want the tangent to be the u, what do I need to be sitting there? Okay, so do you see how this is going to be more difficult than the last one was? Okay, so before that we started off with the more simple case because if you wanted the cos to be the u, then you needed to have one sine sitting there. If you wanted the sine to be the u, then you needed to have one cos sitting there. That was a really easy relationship to recognize. Now that we've kind of practiced it, figured it out a little bit, we're going to do secant and tangent, where if we want a secant to be the u, we need one secant and one tangent sitting there. If we want the tangent to be the u, we need a secant squared sitting there. Okay, so the rules are going to feel a little bit more complicated for this one, but the idea is the same. Okay, all right, so let's go ahead and write this down. So we're doing trig integrals still. But this is secant and tangent this time. So just like with sine and cosine, you're always going to try u substitution first, like regular u substitution, not with the secant tangent rules first. Okay, and then you're going to start going into these rules. So if secant is even, save a secant squared for du, and then convert the rest to tan using the Pythagorean identity. So if your secant is even, you're going to save a secant squared because that's your derivative, and then you're going to convert everything else into tangent. So your goal would be to get the whole problem in terms of tangent and save just the derivative of tangent, so save just the secant squared, okay? So that's if secant is even. So that's one strategy. The other strategy is when tan is odd, save a secant x tan x for du, and then convert the rest to secant using the Pythagorean identity. When tan x is odd, save a secant x tan x for the derivative and convert everything else in terms of secant. Okay, so the trick to remember is that the derivative of secant is secant tan, the derivative of tan is secant squared. Okay, so, and we don't have a power reducing formula for this one, so that's kind of the nice thing. There's pros and cons to each of these when you're doing them. So let's do a couple examples. What example number are we on now? Okay. 5. Okay. All right, so the first problem is tan to the 6th x secant to the 4th x dx. Okay, Okay, so let's think in terms of our derivatives here. So one derivative is a secant tan, one derivative is a secant squared. So which derivative should we save? A secant tan? Or should we save a secant squared? Save a secant squared. If you tried to save a secant tan, then you'd have all odds, and you couldn't use Pythagorean identities to convert stuff all into one thing. Does that make sense? So if we tried to save one of each, then we'd have a tan to the fifth, secant to the third, and we'd be stuck. We wouldn't be able to convert those. If we save a secant squared, then we can take the other secant squared and convert it into tangent. Does that make sense? How we're kind of strategizing there, okay? So we're doing it just like the last time. We're thinking in terms of what derivative do I see present, and then how do I convert the leftovers into the other thing, okay? The derivative I see present is a secant squared. So what I'm going to do is I'm going to take the problem. I'm going to write this as tan, goodness gracious, my lead, tan to the sixth times secant squared times secant squared. So I'm saving one of the secant squareds as my derivative, and then the other secant squared I'm going to turn into tangent. Okay, so I'm going to look at my blue sheet, and my blue sheet tells me that secant squared is okay. All right, do you guys want to turn this into U's and then distribute the tan to the sixth, or do you want to distribute now? Distribute now? Okay, so take the tan to the sixth, and when you distribute, what do you get? Okay. Okay. Perfect. So we can have our u be tangent, and then our derivative of tangent is secant squared. So we've got our u and we've got our du. All right. So u is tangent, derivative is secant squared. So how should I rewrite the problem? Okay. Okay, and so if I take the u's and replace them with tans, what do I get? Beautiful. Okay, boom, we did it. Okay. Next example. Tan to the fifth theta, secant to the seventh theta, d theta. So is the derivative that we have secant squared, or is the derivative that we have secant tan? Secant tan. If we were to take out a secant squared, then we would have all odd exponents that would not be helpful, right? We wouldn't be able to convert all into one thing. So if we take out one secant and one tan, that leaves us with even exponents, which we can then use the Pythagorean theorem to convert all into one thing. See how it's not as complicated as the rules seemed? So I'd say, like, the rules, I copied these notes from another teacher who had taught calculus before me, but the rules kind of complicate things. It makes it a little bit easier if you think in terms of what derivative is present. Does that make sense? Okay. So the derivative that's present is the secant tan. So we're going to take out one secant and one tan. Okay, so if we have secant tan as the derivative, then are we converting everything into secants or are we converting everything into tans? Secants, because secant is what you're taking the derivative of to get the result secant tan. Okay, so we want to keep this as secant and we want to take tan to the fourth, and we have to think of it in terms of tan squared, right? So if you want to think of it in terms of tan squared, how do you get tan squared to tan to the fourth? Tan squared squared. Okay, so I'm going to take the tan squared squared. Are we okay with that? Okay. Tan squared squared. Actually, just kidding. We wanted to... No, you're right. You're right. You're right. Sorry. My bad. I confused myself for a second, but I'm good. Okay. So tan squared squared, that's how we got tan to the fourth. So now I'm going to take the tan squared, and we're going to have to do a little bit of mental math using our blue sheets. Tan squared needs to be replaced with what? Secant squared minus 1. Tan squared needs to be replaced with secant squared minus 1. Okay, so this is going to be secant squared minus 1, and then squared on the outside. Are we comfortable with that? Okay. And then secant to the sixth. Now this is a little bit complicated, so I'd suggest maybe we do it in terms of u before we simplify completely. Should we do that? Put it in terms of u now? Question. Yeah, so that's exactly the process we're going to need to do. Secant squared minus 1 squared, that's going to have to be FOILed. And then the secant to the sixth is going to have to be distributed. And this notation is cumbersome. And students are more likely to make mistakes in this notation. So we can convert it into u's before we do all of that work. So let's go ahead and convert it into u's first. So we'll say u is what? Secant. Du is secant tan. Okay. And so what's the problem that we're doing? Okay. So now the math that we need to do is u squared minus 1 times u squared minus 1. And then once we FOIL that, we're going to distribute a u to the sixth. So when we FOIL u squared minus 1, what do we get? Okay. And then when we distribute the u to the sixth, what do we get? Okay. So what we are actually integrating is u to the 10th minus 2u to the 8th plus u to the 6th du. Okay. Okay. Mm-hmm. Okay. All right, how do your brains feel? Brains feel good? So the trick for these is to look for a secant squared, look for a secant tan. That's the trick. Okay, so the 4 problems